So hello guys, welcome again in our next session of this international webinar series. So as you already know, today is our talk 4, and the topic for today's talk is application of rock mechanics and engineering geology in geoscience and infrastructure engineering. So I'm Ajay Kumar, Vice President of GeoVigyan, and I heartily welcome Dr. Debanjan Guha Roy to deliver this talk. Dr. Debanjan Guha Roy is an assistant professor in Department of Civil and Infrastructure Engineering at IIT Jodhpur. Before joining IIT Jodhpur, he was a DST-INSPIRE faculty fellow in the Department of Earth and Atmospheric Sciences at NIT Rourkela, Odisha. Dr. Debanjan Guha Roy has completed his dual-batched Ph.D. from IIT Bombay, India, and Monash University, Australia. He is also a recipient of Star Fellowship by the Society of Petroleum Engineers, USA, and Duncan A. McNaughton Research Grant by the American Association of Petroleum Geologists, USA. His current research interest lies in the rock mechanics of cryogenic fracking and wellbore failure. So now I would like to call Dr. Debanjan Guha Roy to deliver this talk. Thank you.
Thanks. Let me share my presentation first. Okay, so thanks. As you know, I'll be talking about this application of rock mechanics and engineering geology in geoscience and infrastructure engineering. Now, rock mechanics and engineering geology is not a subject which is normally taught in the universities, neither in the UG level or in the PG level explicitly. Unfortunately, there are only few institutes, mostly in IITs, where this subject exists, but in geoscience departments, they normally focus on the engineering geology aspect and less on the rock mechanics aspect. So we'll see why this is so, and why there are a few other departments who also deal with the rock mechanics aspect, and where geology comes in and where we have an advantage and how we can deal with that. These things we will see. Since the rock mechanics and engineering geology is not taught regularly, so we'll first focus on what they are actually and what they mean and how we use them. So first, if we look at the rock mechanics, we already know the rock. There comes the mechanics part. So mechanics is basically a displacement and deformation of a solid resulted from a force, if we talk about the solid mechanics. So basically, we're applying the principles of mechanics to describe behavior of rocks at engineering scale. Now, that is a new term for us. That is the engineering scale. That is that we don't normally deal with in the geology. We do it in geological scale. So we'll focus on that part later. So basically, in that rock mechanics aspect, we will deal with the stress strain, principal stresses, Morse circle, constitutive laws, failure laws. Now, once you look at these topics, these are something not new to most of the geology students. If you had a class on structural geology, probably you know these topics. So basically, there we use rock mechanics. We use rock mechanics to understand how the faults are being created, how folds are being created. Just like the photograph here. So we already know certain aspects of rock mechanics, but in the subject of structural geology. But the structural geology goes beyond rock mechanics. They also incorporate elements of tectonics and other things to describe the geoscience part. But in rock mechanics, we don't go into that part. Next is the engineering geology. In engineering geology also, we apply the principles of geology to describe engineering scale of behavior of rocks of engineering scale. So the elements of geology are normally the petrology, tectonics, geochemistry, remote sensing, structural geology, and lots of other things. We use those knowledge for the engineering projects. So for example, if you take the problem of landslide, we will see in detail how we do the engineering geology of landslide. But just for now, for an example, if you take landslide and if you see the distribution, we see that in India, most of the landslides are concentrated on the Himalayan region. Now, the reason is because this zone is tectonically very active. Now, the knowledge of tectonics is only with the geologists. So, other people cannot do. Although this construction or the remediation, all these things are dealt by other engineering people. But why these landslides are concentrated on a single belt, that knowledge comes from geology. So, this is where we come in. Now, we have mentioned the engineering skill. So what is an engineering skill? So in the first image, if you look at the plate tectonics, normally we deal with a range around like 1,000 kilometers or more than that. And the time we normally deal with are millions of years. But if you look at the other images of tunnels, mines, both underground and open pit mines, or geothermal energy, or construction of building, or even in landslide, the scale is very limited. Mostly the scales are hundreds of meters. Only in case of tunnel, if you take the length, it might go to few kilometers. So the scale is severely limited in case of engineering geology and rock mechanics when you compare them with the geology. Also in geology, we normally talk about the processes which are going on for millions of years, if not the billions of years. But here, when we deal with the engineering projects, maybe we talk about 10 years, 50 years, and at most 100 years. So this is the main difference between this rock mechanics and engineering geology and the conventional geology that we normally do. So basically, we apply all the knowledges of geology in the rock mechanics, in engineering geology, to successfully construct an engineering project. So who does the rock mechanics and engineering geology? We have seen that rock mechanics is a separate part, engineering geology is a separate part. Now, rock mechanics is basically a component of solid mechanics. Now, solid mechanics is a core component of mechanical engineering, civil engineering, chemical engineering. If we talk about the flow, chemical engineering does many of those things. Mining engineering, hydraulics and water resources engineering, and geology and geophysics. So whenever we talk about the rock mechanics, we do research or any work, we actually work alongside those people because they do have very good knowledge of solid mechanics if we deal with the solid. If you are talking about, suppose, hydrocarbon, where the hydrocarbon is inside a rock, a porous rock, then there is also a component of fluid mechanics. So they also do the rock mechanics along with us. But when we talk about the engineering geology, where you need the knowledge of geology, a geologist can only do that, not even our geophysicists. So here we have the knowledge. Now in this diagram, although I have shown the rock mechanics and engineering geology separately, as we do rock mechanics, we will see that these two topics are not really very separate. We get the knowledges of engineering geology and we put them back in the rock mechanics to study the mechanical behavior. So these two are very closely related subjects. So whenever there is a rock mechanics problem in the practical life, we have to have a knowledge of the engineering geology. And here the students of geology and geophysics have an advantage over a civil engineer, even over a mining engineer. So when we talk about the geology and the geologists, we have certain skills that people don't have. Particularly in the range of mapping, we can do field work, we can build topographic map, we can do remote sensing and GIS, and we can collect geological information. We have the ability to do the large-scale interpretation, particularly in tectonics. We can talk about the geological processes. We can talk about the rock properties, particularly the petrology, the physical properties, and mineralogy. So these are the advantages that we have whenever we are dealing with any type of rock. But the major disadvantage that the geologists have, the knowledge, the information, the description that we make, those are essentially qualitative. We love to write big paragraphs that gives us a bigger picture, but it does not say quantitatively what is the strength of this rock, or it cannot say whether this rock will stand for next few years, or when this rock will be weathered down. Now, whenever you are doing an engineering project, you don't work alone. You have to work with the designers, engineers, and lots of other people. So to help them designing certain structures, to help an engineer to understand what are the strength or the fracture parameters are working, you need to be very quantitative. And this is where we need to have an advanced knowledge of rock mechanics and engineering geology. And we'll talk how we get those numbers. So a geologist needs to know the number or needs to know the process to how to quantify certain processes. So this rock mechanics and engineering geology is a very multidisciplinary topic. It is practiced by all the engineering disciplines and it is practiced across different domains for different purposes. For example, if you talk about the mining engineering, they use rock mechanics to understand the blasting, to understand the dump slope stability, to understand the underground space technology. In case of oil and gas, in reservoir engineering, they use rock mechanics to understand hydraulic fracture propagation, to understand wellbore stability, the reservoir depletion. In geology, geophysics, we directly use to understand tectonic processes. For example, you can actually model the plate movement using the rock mechanics knowledge. We also use them for landslide analysis. We also do rock mechanics for carbon geosequestration. In civil engineering, we use extensively engineering geology before we make any plan or design for building or bridges. We do the same thing in case of tunneling or building a long highway. The domains you see highlighted here in yellow, I'll be talking about them. I'll not talk about the rest of them, but you will get a good understanding how vast this domain is and how many information you need and how a geologist can contribute in that. So we can start with the underground space. Now, if you have seen the Avengers movies or specifically the Black Panther, you must have seen this image where they have the Shuri lab, the lab of the Wakanda. And the lab inside looks like this. This is an example of underground space, although from a fantasy land. But this is not really a fantasy. For example, if you see the first photograph of a stadium, it looks like a normal stadium. It's an ice hockey rink, and where they play Olympics. Now, this is a big stadium, but the fact is that it is not equivalent to a normal stadium, cricket stadium that we see. It is not Eden Gardens. It is actually an underground stadium. It is underground, it is below a mountain. You cannot see the entire image of the mountain, but it is built underground a mountain where the span of this stadium is around 62 meters. And total 140 to 1,000 meter cube of rock was excavated in 2 years at the cost of 20 million. But whenever they're designing it, they have to have a very good knowledge of the geology of that area. Why? Now, suppose you are building this big structure within a mountain, and this is in a seismically active zone. Now, if there is a seismic event more than 4 or 5 in Richter scale, the structure would eventually collapse, which is a health hazard. Now, suppose it happens during a game, there will be thousands of deaths. So they have to have a good understanding whether that area is seismically active or not. Next, even if there is a seismically active, we have to know whether the rock you are going to excavate is a massive rock or there are some natural joints or fractures. Because as you might understand, under loading, under kind of stress, a rock with fracture will get activated. The rock will move along the fractures. And once it moves, a solid structure will break down and cause accident. But what if there is a groundwater problem? You know there is a groundwater table, and if you excavated a hole below the groundwater table, the groundwater will rush towards this place. So you need to have a good understanding of the groundwater table and how the table varies with season. During suppose monsoon, although in Norway we don't have the monsoon, but the groundwater table do change over time. And all this knowledge must tell us about the strength, because depending upon the strength, you need to put the support structure. So this structure, this underground space was built in Norway back in 1980 probably. So they have gone long ahead of us in building underground structure. And all those information are collected by geological mapping, doing lab scale tests, and doing numerical modeling. And geologists and civil engineers, they do participate in that. Next, this is an example of underground seed vault. This is a famous seed vault where they actually preserve all the types of seeds from across the world. They collect seeds from India to North Korea to America, and they preserve for doomsday in case there is a drought or there is a large-scale catastrophe which will will destroy our agricultural lands. They can actually get the seeds out of these vaults and regrow plants. And it is built inside a mountain. It is built inside a mountain where they can keep it frozen, they keep it safe, they can keep it safe from natural events, they can also keep it safe from terrorist activities. Because as you know, in many cases, different state and even terrorist organizations can also attack and bombard this place. So they have to make it safe so that it can even withstand the power of a nuclear bomb or similar type of explosion. So to have all these things, they have to have a good understanding of what type of rock they are going to excavate, whether there are faults or joints, What are the seismic activities? What is the groundwater condition? And this is where engineering geology and rock mechanics would come into picture. They would talk about the strength of the rocks, whether there are going to be any failure during construction, there are going to be any water seepage, or what type of design and support you need to have. Next is about the nuclear energy. Now, we know nuclear energy does not have any kind of emission, unlike our coal-powered power plants or other kind of energy sources. So this is a green energy source. Unfortunately, it is not always very safe, as you have already seen in case of Fukushima or before that in Chernobyl. But beyond this immediate risk that there are with the nuclear power plant, there is one other risk people normally don't talk about, which is the nuclear waste. Whenever you have nuclear energy generation, the entire fuel is not used. There are some products which come out of this nuclear energy, which itself are very radioactive, and they are very hazardous. They have very high amount of radiation, and you cannot just dispose them into groundwater or in underground place, something similar to other the construction materials that we do, because they have high amount of radiation and they contaminate the soil and water for a very, very long time. And once those soils and places are contaminated, you cannot reclaim them back. And at present, we don't have any method to deal with them. We don't know how to treat those waste and how to process them. So, but you see, if we don't know how to treat them, but we are still running lots of nuclear power plants. So what are we actually doing with the nuclear waste? Now, in the nuclear waste, if they are radioactive, they are very hazardous, then you have to keep them safe somewhere. So at present, what people do, they are designing underground spaces to keep those materials safe. But those safety chambers need to have very high safety requirements. Because at present, we don't know the process, how to deal with this. So we're still actively researching on that. So those nuclear wastes have to be preserved for like more than 100 years. They have to be away from the public land. First reason is the contamination. Second part is that this nuclear waste has nuclear material. The terrorist organization, if they have access to those nuclear material, they may not develop a full-scale nuclear bomb, but they can develop a bomb called dirty bomb. They can drop it in a city, they can contaminate the water and kill thousands of people. So it has to be safely preserved somewhere away from the public reach. Also, it has a high radiation. It has a very high temperature. So we have to ensure that there is no leakage in that underground space so that this radiation cannot contaminate the groundwater. And this is why International Atomic Energy Commission has stringent recommendation how you should build this underground space. And few of the recommendations are that it should be radiation protective, there should be a method for removal of heat, there should be an emergency procedure for ventilation. And these are only three. I have given the source here. One can go in the source, you can see how stringent the recommendations are. So to consider all these things in design, we have to find a place. And for example, here in Yucca Mountain in USA, they have found a place and they have designed a nuclear repository. And the preliminary investigation was done by the geologists with the help of geophysicists and mining engineers, and they have designed this entire space. So, for example, that we have talked about in this Yucca Mountain, we have seen the temperature is very important. Now, here I have given you an example from my PhD work, and we're talking about the fracture toughness. The fracture toughness is basically how the rock will fracture over time. And if you see, if a rock is exposed to high temperature, starting from the room temperature to 800 degrees, the rock fracture toughness vary. There are multiple fracture toughness, mode 1, mode 2, mode 3. We will not get into that. But you will see, depending upon different type of rocks, starting with granite to sandstone, the fracture toughness do vary. So rock mechanics or engineering geology researcher has to have a good understanding of this part. Next, if the rock is anisotropic in nature. Now we know all rocks are not homogeneous. We have gneiss, schists and everything. And depending upon the underground space that we're going to design, this anisotropy can cause failure. For example, here again, if we talk about the fracture toughness, we see that as the anisotropy angle is changing, the fracture property of a rock will also change. So these are the things that we study in rock mechanics and engineering geology whenever we are dealing with the underground space. Next, if we go into the reservoir engineering, we have a process called hydraulic fracturing. So hydraulic fracturing, basically, it is done in case of shale gas and oil extraction. As you might know, shale rock is very dense, it is highly porous, but it does not have appreciable amount of permeability. And if you want to extract oil out of it, you need to have a highly permeable rock. In those cases of rock, we actually forcefully send a very high volume of water along with several chemicals, and we forcefully fracture the shale rock. Here you can see we are sending this propans through it, and we are fracturing the rock here. By fracturing the rocks, we are creating permeability pathways. These are open fractures through which the oil will flow. But the question is, what strength does this rock have? Because as you know, you have to at least have a certain force to fracture a rock. So when you do hydraulic fracturing in oil and gas, you need to have certain basic understanding, like what is the minimum principal stress, and what is the direction, and what is the strength of the rock that you are going to fracture, because this strength will determine how much mud pressure you will be using in oil and gas. Then, as you know, there is already hydrocarbon inside a rock. Those hydrocarbon has also its own pore pressure. So you need to know what is the pore pressure, because if the pressure you are putting here, less than the pore pressure, then as soon as you fracture this part, this hydrocarbon will flow, and you cannot maintain the stability. It will go up and cause a blowout. As you might know, few months back in Assam, we had a blowout. We had multiple deaths and millions of dollars were lost. So no company will allow this blowout to happen, and you need to have a very good understanding of the pore pressure even before you start the hydraulic fracturing operation. Next, even if you do hydraulic fracturing, you're doing it like 1 or 2 kilometers below the Earth's surface. Now you need to have a good understanding how this fracture will progress. Now you see here, there are 4 or 5 layers, and sea water table is here. Now suppose this bed is quite close to this water table, and while you are doing hydraulic fracturing, you accidentally fracture this water table. So all the more than hundreds of carcinogenic compounds that you have used for hydraulic fracturing will get into this water table, and this water cannot be used for drinking or any other purposes. There have been cases where thousands of kilometers had to be abandoned because this groundwater was contaminated by the hydraulic fracturing. So all this knowledge regarding this rock behavior, the principal stresses, they must come from a geoscientist. And the rock mechanics engineer is the one who gives this information to the reservoir engineer so that they can model the geomechanics of that domain or the rock mechanics of that domain beforehand. So now geomechanics and the pore pressure engineer are 1 or 2 hot topics in the hydrocarbon industry. So in any case, if you want to go into hydrocarbon industry, this would be a good place to go. And once you do all this modeling, you know all the knowledge, you can actually also predict how much hydrocarbon you will be getting out of it. So this is a fascinating area of rock mechanics when you deal with oil and gas. Next, we'll go into our engineering geology problem called the slope stability problem. You must have already heard of the landslide issues in many domains. For example, here I have given an example of landslide in Maharashtra that is known as the Malin landslide. Over a night, this landslide happened over a village and more than 100 people died. And this is one problem we face not only in Maharashtra and across many domains, specifically in the northern part. For example, here in Jammu Kashmir, we had a landslide an entire section of road was wiped out. And here engineering geology plays a very important role. When we talk about the rock, if you see this happened over a certain kind of geology where there are rocks, there are soils, there are weathered materials. Here you see we have explored rocks. So whenever you are going in a certain place which is vulnerable to landslide, people ask such conditions like what is the influence of different types of loading conditions on your rocks? What if there is an anisotropic of rocks or different rock beds? What will happen if there is a monsoon or there is a very high rain? Also, there is a rise in the groundwater. What will happen if there is an earthquake? What will happen if there is a freeze-thaw cycle? This is basically happening at the higher reach of Himalaya where you have ice which is freezing at one time and then melting in other seasons. Now, suppose you have rock where there is only one joint and the joint is exposed. That part can fail if there is any earthquake or there is a freeze-thaw cycle or there is a very high water pressure. You can have also different type of failures. This is called the planar failure. This is wedge failure. This is toppling failure. And whether this failure should happen or not can be studied using stereographic projections. Now, we geologists already know how to do stereographic projections. If we plot the poles of these joints, we can actually identify the vulnerable areas and we can make predictions whether this rock is going to fail or not. This is an important aspect of engineering geology which a geologist can do. Now, this is one example. Again, I'm taking from Avengers. This is the mansion of Tony Stark, who is the Iron Man. Now, if you remember or if you see this photograph, this entire mansion, this heavy load is on top of a cliff. If you remember, in front of this, there is an ocean. This is a slope, example of a slope on which you are making a civil engineering construction. Now, the point is, this rock can be jointed. This rock can be massive, or this is not, might be entirely a rock. Portion of this might be a rock, on top of it there will be weathered soil. The question is whether this entire mansion will remain stable over time or not. And this is not just a fantasy, this thing happens. For example, I don't have the photograph yet, but in Oman, one very rich person is actually making a similar mansion inspired by this Tony Stark's mansion. And there is one Indian company who is delivering this rock mechanics and engineering geology service. So to study these things, we can take many approaches. We first do the geological mapping. We identify all the vulnerable joints and maps. We also do lab-based testing to understand their strength properties. We also do a few more interesting things like physical modeling and numerical modeling. This is basically a lab-scale modeling of a particular slope, whichever slope you are interested in. And this is the load similar to the Tony Stark's mansion. And you see, these are the layers people have made, and they change the properties. For example, they change the loading condition. Depending upon the size of the construction, they can change the slope angle. As you see here, they can also play around the spacing of this material, and they can study whether this particular slope will remain stable or not. But as you understand, in lab, we have several limitations. We cannot replicate the natural condition completely, particularly when we have to talk about the principal stresses and large-scale faults. We cannot do them in lab. In that case, we try to do them mathematically. And mathematically, we basically deal with the differential equations, which are dictating how a rock will behave under different kind of loading conditions. And we do the numerical modeling. And in numerical modeling, actually, we can study different scenarios. What if this is the normal slope that we're dealing with, and if we cut the slope, what will happen with the stability? How the joints will get activated? You see these colorful patterns, they show the deformation. So basically, we can change the loading condition in our computer. We can see how a geological media will behave over time. So this is how we do landslide or slope stability analysis. We can also do slope stability analysis over a big horizon. So similar to earthquake zonation map, we can do landslide zonation map. So this is one landslide zonation map developed by the National Disaster Management Authority of India, and they show where the landslides are concentrated. And you might not be very surprised, because you all are geologists, that geologically active parts are mostly landslide prone. And the entire area of our Himalaya is highly landslide prone area. But this is a very large scale and national scale map. But you can actually do this map in small scale, like in a district level map. Here is one example of a Chamoli district from Uttarakhand, where they have done the remote sensing and GIS based landslide zonation map, and they can actually identify the slopes where the hazard is very high. You see this mountainous slope, and where you have these red portions they are susceptible to failure. So in case you are trying to build a road there, you want to build your house there, you have to be very careful where you are building them and what precautions you have to take. So a geologist, an engineering geologist, will transfer this map to our civil engineers or infrastructure planners to give them the idea what type of material they are dealing with. This type of maps are also available with our disaster management authorities, and disaster management authority can be engineered or our decision makers or policy makers, so then they can build overall policy. And thus engineering geologists contribute to the bigger policy making picture of country or state. Next, we'll go into a process called the carbon geosequestration. Now, as you know, the greenhouse gas emission is rising like anything. And India is one of the top 3 emitters. And this, as our economy is progressing, we need more energy, we are emitting more carbon dioxide than ever. And this carbon dioxide mostly comes from the electricity. Electricity means the coal-powered power plants and other sources like construction, manufacturing, and agriculture. But we cannot let this happen for a very long time, as we know already the problem of Delhi pollution. Now, this similar type of pollution is everywhere because Delhi is the capital, so you get to know about the knowledge. And there is actually a study which shows that there is actually a decrease of around 2 years of any person's life with this type of pollution. So what we try to do, we try to do a process called carbon sequestration. We take carbon out of the atmosphere and try to bind them using chemicals or other different methods. Now, geology plays a very big picture in that. We can actually get the carbon dioxide directly from the coal power plant and put them back in our geological sequences. So basically, you have a power plant somewhere in India, you take all the CO2 it is created, but instead of emitting it out in the atmosphere through pipes, you can store this carbon dioxide in multiple places. Now, there is another aspect of storing CO2 in the geological media. There are certain advantages. For example, whenever we talk about hydrocarbon production, initially we produce hydrocarbon by creating a pressure difference in the wells. But over a time, this pressure difference between this hydrocarbon bearing rock and here is decreased. At that time, we actually inject CO2 or inject high temperature water to push this oil towards our producing well. So if you do carbon geosequestration, in case of a hydrocarbon reservoir, you can actually injecting lots of greenhouse gases here, and you are taking back lots of oil here. So the cost you need to put the carbon dioxide here you're getting some money back from this place. Similarly, you can do the CO2 geosequestration artificially in coal mines. You can do in coal strata or saline aquifers. In India, Coal India and ONGC are working, and NTPC are working on projects to geosequester the CO2 in different Gondwana coal mines, Gondwana coal strata, and they're also trying to use this CO2 to get the CBM out of it. So this introduction of CO2 will help to get ECBM. This is called the enhanced coal bed methane recovery. So this is a win-win situation, and India is investing heavily in carbon geosequestration. But to do this carbon geosequestration, you need to know the good geological understanding. You need to have a very good geological understanding about the coal, about the saline aquifers, about the hydrocarbons, the pore structure, and all these topics are covered in geoscience. So the rock mechanics researcher from geology or geophysics will be involved in this type of work. Next and last, we'll be getting into the tunneling. Now, this is a photograph of Atal Tunnel, which was inaugurated recently by our Prime Minister. Now, this is a fascinating piece of infrastructure work. This is a 9.02 kilometer length of tunnel, which work started in 2009, and it was supposed to be completed in 2015. However, the work got delayed in 2020. In India, many government works get delayed due to this bureaucratic process. But this tunnel was not delayed because of that. The reason of delay was high ingress of water. The volume is 125 liters per second during building of this tunnel. Now, this is a very, very important problem whenever you are doing tunnel. If you have a river passing through it, it can send water to your tunnel that you are building inside a rock. But if you also have shear zones, as you know, shear zones have very high permeability compared to the rocks around it. So if you have water, if you have surface water or even rainwater, they can actually enter the tunnel. It will collapse your tunnel. It will stop further movement. And Atal Tunnel faced the same problem, which delayed it for 6 years. So we had to mitigate this issue, and then we could build this tunnel. But apart from that, when you are doing tunnel, you have to have an understanding of the seismic activities, whether this tunnel will going to collapse or not. And to do this, geologists do tunnel face mapping. Suppose you first build a 10 meter of the tunnel, then you have a rock in front of you. A geologist would map the face. A geologist would study if there are shear zones, if there are joints, what type of rock they are facing. As you know, over 9.02 kilometers, maybe you can face hundreds of types of rock and rock strata with different strength, different type of joints. These joints can have different deep and strike angle. The joints can be open, they can be filled with quartz or calcite. All this information a geologist needs to note down. And once they note down, the next phase of tunneling starts. So we play a very important role. An engineering geologist will play a very important role. Not only during the construction of the tunnel. Suppose this tunnel has been built, and after 10 or 15 years of operation, some place of this tunnel collapses. And we have to reinvestigate the old geological map. The geological map the engineering geology has prepared during construction of the tunnel to find what went wrong. Did we miss any shear zone? Was there any seismic event that we did not predict? So this geological map, this engineering geological investigation report is very important over the lifetime of a tunnel. Apart from this tunnel, we are also building tunnel in the cities. For example, here is one example of Mumbai Metro. In Mumbai Metro, as you know, similar to Kolkata Metro, is mostly underground. Now, whenever they are doing underground, Mumbai is already a very congested place. It has very congested high-rises and buildings which have very poor foundation, and they were built around like 40 to 60 years from now, 50 years back. So whenever you are building a tunnel below a thriving city, the most populous city, you have to be very careful. You cannot, whenever you are doing tunneling, you cannot create cracks or anything like that, or you cannot disturb the zone just below your buildings. And there is no way that you can evacuate people from here and do the tunneling. So you have to do the tunneling and build all these holes while people are working here. To do this, a geologist first needs to do survey. Now, as you can understand, whenever you take a profile, first you will encounter soil. There are soil classifications where engineering geologists will work along with a geotechnical engineer who is from a civil engineering background. So first they will do the soil survey. Then if they encounter rock, an engineering geologist will prepare a geological report. They will prepare the geological report of the rock they are facing along the length of the tunnel as well as the vertical sections. So, for example, here they have prepared a tunnel in the area of Girgaon and Kaldevi, and they did not build a tunnel by simple blasting method. What they did, they used an instrument, a very expensive instrument named tunnel boring machine. So basically, this is a rock cutter. It is cutting through the rock, and they drop this tunnel boring machine in the place where they want to build a tunnel, and this face rotates, and you see these small circular parts, they cut through the rock. A geologist need to give the total geological map of this area even before the tunnel boring machine consultants are contacted. This is because the structure of this area will determine how much a tunnel boring machine can actually penetrate. So these are very expensive machines. The operations are very expensive, but the amount they penetrate every day is very small. They can hardly go 1 millimeter per day because of the complexity of this operation. So geological map and rock mechanics report, they play a very important role here. Now, the strength that I talked about, the fracture toughness or the report, they have to be done in separate ways. You have to do geological mapping. That is a fieldwork that you are already aware of. But the next, when you get rock sample, you need to have strength, and that we do in our laboratory space. Now, since rock mechanics lab is not a common thing in India, so I'm skipping the geological map part that you already know. But now we are going into the lab work. So in a rock mechanics and engineering lab, we'll have many instruments. The first one is called the UTM machine. UTM machine looks something similar to that. You can have a variation of this machine. The UTM means universal testing machine. It is also called CTM or compressive testing machine. This is a rock. You take a rock, you cut a cylindrical piece out of it, and then you try to load it. So basically, these are called platens, where you keep this cylindrical rock, and then you push them. You push them up from up and down to put a compressive load, and you see when it will fracture. The load at which this rock will fracture is known as the compressive load of that rock. So this is the closer look where you see these instruments are normally we put to measure the Young's modulus and the Poisson's ratio of a rock, and we do decompressive testing. Now you also know about the Mohr circle. Before that, suppose your rock is anisotropic. So the compressive load will depend on the anisotropic of a rock, how the bedding angle is varying. So these are the things normally we study. Next, we do an test which is called the triaxial test. So when you are talking about tunneling or some underground space, you know that there are principal stresses. The rock is confined. There are sigma 1, sigma 2, and sigma 3. And as the compressive load, but the confining load will increase, the strength of a rock normally goes higher. We can replicate this process in our lab using triaxial test, where an instrument, a triaxial machine and triaxial cell is used, which looks like this one, where we use confining stress. So if you take a cut through this instrument, this will look like this. So basically, this is your cylindrical rock sample. You have oil around it. So this oil will be compressed and will give you the required amount of confining stress. And then you put the load from up and down and try to fracture the rock. So for different value of confining stress, those are sigma 3, you will get different amount of compressive load, that is the sigma 1. And from that, for different confining stress, you can build the Mohr circle. And from the Mohr circle, you can measure the internal angle of friction and the cohesion of a rock. And also, as the rocks undergo different amount of confining stress, from the Mohr circle itself, you know that the fracture pattern would change from here. And the rock behavior can also change from brittle to ductile. So this is another very important test that we do. And these instruments are very costly. For example, a simple UTM would cost you around 10 to 15 lakhs. These small parts, this small part will cost you around 2 to 3 lakhs. And for triaxial instrument, that can go up to 40 to 50 lakhs. So this is a very specialized and very expensive affair. And this is why probably in India, we have very few labs doing this type of work. Next, we also study the ultrasonic velocities. So ultrasonic velocities are basically the P wave and S wave in a rock. As you know already, P wave and S wave, they talk about the density and everything. We can actually measure those velocities in our lab. So in lab, we normally take a cylindrical sample. These are called rock cores. We know the length of the sample. We put a transducer and receiver on both the sides, and we send a signal, either P wave signal or S wave signal. And from the time it takes to go from one end to another, we can calculate the velocity from the length and the time. Now, as you know, this is equivalent to seismic velocity. We do large-scale seismic testing, we get these seismic plots, but between this lab-based experiments and seismic, the field-scale seismic, there are a few differences. For example, in lab, we often use high-frequency transmission. So those give the dynamic measurement. But in field, we use low frequency. In that case, those are the static. So we need to be careful how we extrapolate the lab result to our field result. And why we are doing this kind of ultrasonic velocity measurement? The ultrasonic velocities, those are the P wave or S wave, are actually related to the porosity of the rock. It is related to the density of the rock. It is also influenced by the fracture or existing joints of the rock. And it can also give you information how strong the rock is. For example, these are a few results I'm showing here, where you see the velocity plot on the Y and the porosity plot of different rocks on the X. As you see, the porosity of the rock is going higher, the velocity is decreasing. But if you have another rock, as the density is going high, the velocity will get higher. Similarly, if you have rocks where the strength of the uniaxial compressive strength of a rock is going from low to high, the velocity will get higher. So from studying the velocity, you can actually have a good understanding about the porosity, compressive strength of the rock. So in many times, we can use different equations to find the strength of the rock from the velocity itself. So we might not have to do this type of expensive testing to get an understanding of the strength of the rock. So I'll stop here because these are too much of things. So these are the lab experiments normally we do. A rock mechanics and engineering geologist, geology researcher would do. So there are, I say, there are quite a few institutes which are engaged in type of research. And since you have already seen the rock mechanics is dealt by mining engineers, reservoir engineers, as well as geologists. So here are a few institutes in India who are engaged in this type of work. You will notice we have departments like earth sciences, we have civil engineering, mining engineering, geology, in IIT Dhanbad, mining engineering, earth sciences, reservoir engineering, all are involved in this type of work. So in case you are interested, you can visit their lab and you can see what type of work they are doing. Not every department is doing every type of work. For example, earth science in IIT Bombay is focused on shale gas, carbon geosequestration, similar in IIT Kanpur. But civil engineering in IIT Delhi, they're in the rock mechanics. They're actually designing a tunnel for our armed services. There are mining engineering in IIT BHU who are involved in nuclear depository research. We have a geology in IIT Kharagpur who are on the slope stability work. Similarly, in IIT Rourkela, we have rock mechanics in civil engineering, rock mechanics and engineering geology and earth sciences. They are working on the landslide problems. In IIT Dhanbad, they are working on most type of research works, for example, in hydrocarbon, hydraulic fracturing, mine stability, and similarly in other areas also. So you can go and see what type of works they are doing. So I'll stop here and thank you for joining. So now if you have any question or anything, then I can.
Thank you so much, sir, for to deliver this beautiful talk. I think this was an excellent presentation, and we also have learned so many technical terms through this talk. Now we will move further towards our question and answer session. Sir, I will paste the questions asked by participants in the chat box of our Google Meet so that you can read and answer them without any disturbance.
Sure.
So now you can read.
Yeah, what is reverse hydrofracturing? Reverse hydrofracturing, I don't know if it's a term. I have not heard about reverse hydrofracturing. But if you are talking about like if there is a permanent hydrofracturing, we put a very high pressure of water so that it overcomes the strength as well as the pore pressure of the rock. Now, in case if that is not happening, if the pore pressure is higher than the hydraulic fracturing stress that we are using, then probably the hydrocarbon would flow towards the well. So it might be called reverse hydrofracturing, but I have never come across this terminology.
So
Well,
you
in
can read.
Central Himalaya, the biggest issue is, as far as I understand, is the earthquake. The first thing is the earthquake. Because of these large earthquakes that are happening and they're regularly happening, those are threat to the stability of the underground structure. Next problem is it is not geological problem. Geopolitically this part is very active, and we are sharing borders with many people. So probably it is not a good idea to build there. But high-grade metamorphic rock is a very good candidate for an underground space creation. So yeah, this is the positive point. Is the role of engineering geology landslide risk. So first investigation of any area of any landslide area is done by a geologist. You have to build the geological map. You have to talk about the rocks you are facing there, the kind of shear zones or faults are there. If you identify any vulnerable place, then you have to build this geographic projection. You have to identify the zones where the different type of failure can happen. So this is the first one, and how it can help in reduction destruction. So, I don't know if there's model for reduction. No. So there are model of landslides. So depending upon your orientation of the joints, your groundwater condition, you can have planar failure, you can have wedge failure, you can have topple failure. And once you identify those vulnerable slopes, you can take different remediation measure. That we can do using geological knowledge. So in mining engineering, I'll again probably show the areas. So in mining engineering, they used to design blasting. So as you know, in open pit mining, they use blasting to blast out the wedges, and from that you get the ore. So in rock mechanics, and engineering geology knowledge is used in blasting. Apart from that, you have dump slope stability. So the material you are excavating from one place, you have to keep it in another place. So in policy-wise, there is a very stringent requirement that you have to find your dump places first before even if you start excavation. So you build a small hill of those material, excavated material, and you put it there. But as you increase the height of that dump, it starts failing. So that's the stability study you have to do beforehand. In which places we can do carbon geosequestration. So as I talked about geosequestration, you can do multiple places, starting with normal sandstone reservoir from which you are already producing oil. You can do saline aquifers where you cannot like produce water from it. You can permanently trap those carbon dioxide there. You can use that in coal where the coal is also having the CBM in it. So these are the multiple geological places where you can do. Is it possible that CO2 sequester can be converted to coal? No, it cannot be converted in coal. In coal, normally CO2 is absorbed on its clits. So it still remains in a supercritical form or another fluid form, but not in coal. Well, freezing of water is not always possible because it depends on the temperature and all these things. I don't have the details there, but of course it is a function of the temperature there. So I'm not sure why it did not freeze. When can you have metro in Delhi or no? Well, I cannot talk about the Delhi metro. I don't have much idea about there. But in Delhi metro, see, in most of the metros, we normally face soil more than rock. Whenever you have these 2-3 floors underground, then possibly we will encounter rocks. But I don't have any idea about the timeline. How geothermal energy is generated? So in geothermal energy, basically you have underground rock, which is at a very high temperature. Probably it is because very close to your magma chamber, which is normally happening in Iceland. You fracture the rock, you send a fluid, normally water, which is at the room temperature. But whenever this fluid will come in contact with this high temperature rock, the temperature of the fluid will also go high. You take this water back again and then use that heat. So this is the normal process of geothermal reservoirs. What you can do there is that you can actually do hydraulic fracturing there. You can do hydraulic fracturing, it will open more spaces. You can get more high volume of high temperature water from it. This is also known as enhanced geothermal energy. What is the alternatives of coal fuel in thermal electricity? I don't see any, well, like at present there is no alternative. People are using natural gas to generate electricity, but still in India and China, we are using coal. Anything else?
Sir, I think there is no much more questions to ask. This is the end of our question answer session. So thank you so much, sir. Again, now you can now we can wind up the session.
Thank you for having me. Have a good day. Bye.
Thank you.